It's my pleasure to introduce to you this morning your speaker, now Suzuki.
Ahead of time though.
Oh, you got a couple. Well, you can start early.
Okay.
You want the 4 minutes? Okay. Now came to us as a postdoc almost 6 years ago. This fall it will be. His background was in doing some interesting fits to quasar spectra, and he transitioned very nicely into supernova research here. So now is what we call a postdoctoral fellow. That's where he started. And now you're a research scientist, I guess is your official title here at the lab. Now is the holder of for at least the next few months, the most precise measurement of the cosmological parameters with a paper that came out in just the past month, I guess. It's not even 1 month old.
It was accepted
accepted
last week.
Last week, okay. So it was
So it's
put
official.
out, so a good turnaround by the referee. And it's measurement using supernova as distance indicators, as Io discussed yesterday, using the Hubble Space Telescope. And now is going to give you a lecture this morning, what he entitles A Tour of the Universe, so that you get an understanding of everything that's out there, or at least most of it. So here's now.
Okay. Thank you very much, Peter, and it's a great pleasure to be here. So today I'm going to be discussing the tour of the universe. Tour means in both ways. One is in time, and then one is in space. So I'm going to take you from here to the end of the actually, I would say, edge of the universe, and then from here to the beginning of the universe. So the universe is so here is today's menu. So travel in time and travel in space. You might have heard space-time, which is inseparable. So Einstein made a connection. Indeed, time and space is the same thing. You know, if you are away 1 light year, that means you are 1 year away from there, and 1 light year away from there means in two terms in the same thing. And I'm going to show you what is going on at this lab and what kind of research we are doing. And then I'm going to briefly mention future plans. Yep. So here, we are not using the big facilities, but we don't need to always use the big telescopes. You can observe something very, very fun just from your naked eye. And something special is going on in this picture. Can anybody tell what is going on? So I took this picture one of these days, and something special is happening. You know it. Anybody? Just observe and find what's going on. Come on, guys. You know it. I can give you a hint. Something about the shape of the shades. So on this special day, something special is happening. Astronomical phenomenon is happening. And I want you to tell me what's going on. Say that again? Yeah. But do you know why? How do you know? Okay, go ahead.
Are those pinhole projections?
Yeah. Right. So you see crescent shape, right? So this is a pinhole projection of the sun. So the sun, if you take a look at the telescope, the sun is in a good shape. I mean the crescent shape. So next time the solar eclipse happens, I want you to not only look at the sun, but also look at the ground, so that you can see the pinhole camera image. Yeah? The same thing is happening. So if you pay attention to this, everything in a crescent shape. Okay? So normal day it's just whole sun is round, but on this eclipse day it's a crescent. Okay? And then I suppose you may have a chance to go camping over the summer. And then if you are flexible, I want you to pick up the special dates, which is August 12th through 13th. And then here it's a special day for shooting stars, and then you might be able to see 50 shooting stars per hour. Okay. So at the morning, you can see lots of shooting stars happening. So if you get a chance, look up the sky in the morning, like 3, 4-ish, and then you can see lots of stars. Okay. Okay, so let me start travel in time. So, do you know the age of the universe? Does anybody know age of the universe by now? So when I was a high school student, I was told the age of the universe is between 10 billion years and 20 billion years. But now we know precisely how old it is. Excellent. So 13.7 billion years. So that was measured about 7 years ago, and it becomes more accurate, and we are now sure it's 13.7 billion years. So what would you say the 10 biggest events happened in the universe? Big Bang, of course. And then here is my list. So say Big Bang, of course, and the Big Bang nucleosynthesis, which is the first of the elements. So this is my listing. You don't need to agree with me, but I would say this is one of the 10 biggest events. So so at the very beginning, energy was pure energy. So we didn't exist, of course. And then element, which you learn somewhere, in this classroom has a table of elements, but element itself didn't exist. After 3 minutes, the element was formed, and then say a birth of the first star, and then a galaxy is formed after the first star, and of course our solar system was formed, and the life form appeared on Earth, and the first animal appeared, and these events, right? Animal begins to colonize on land, so this life form had happened in the sea, in the ocean, and now we know extinction of dinosaurs, and we appeared finally. So this is called the Sagan calendar, cosmic calendar, and we translate this 13.7 billion years event into 1 year. So suppose we witness the Big Bang at the beginning of the universe, a Big Bang as the January 1st midnight, and they say we are at the December 31st, close to the midnight. So we're going to shrink 13.7 billion years into 1 year. Okay? So this is in the Carl Sagan's book, he did it, but back then, about 20, 30 years ago, back then he didn't know the age of the universe, but we know exactly when it happened, and then last 10, 20 years, we made a big progress. So we didn't know when the first star was formed and galaxy was formed, but now we know a very good idea when it happened. So once again, say a Big Bang happened January 1st, then Big Bang nucleosynthesis happened right after that. So Big Bang nucleosynthesis means the universe was pure energy, okay? As Einstein's theory says, energy equal mc squared. So energy could become matter, energy could become photon. So the pure energy got separated into 2 forms, which is one is photon, one is matter. Okay? So after 1 second, pure energy got separated into 2. And then one of them became atomic matter, which formed us. That happened 3 minutes after the Big Bang. Okay. So on the New Year's Day, about 10 a.m., the first star was formed. Okay. So first star is believed to be a gigantic star, which is a couple hundred solar mass, bigger than the sun solar mass. And then after that, we believe galaxy is formed, and the galaxy is made of a few hundred billion stars. And do you guys have any good guess when it was formed? Come on, guys. My question is, okay, in this scheme, when galaxy was formed? Okay, it's much, much later. So it took a little bit time to form, structure in the universe. Okay, and the solar system is. After? Yes, of course after, but
a week after.
a week after, okay. Much later, actually. So this is the end of the August and the end of summer. So it took a while to form the solar system. And first life form, you have to create the Earth after to host the life forms. Anybody guess?
December.
Okay, somewhere in the back. I want to hear somebody's voice. Come on, Ray. December? It's a little bit too, but it's not that bad. It was September. But the first life form is kind of a very primitive form, and it took a while to have animals on this planet, and the animal will be December. So from the first life form to the first animal, it took a while. Okay. So to be the exact calendar, so the solar system was formed how many billion years ago? Does anybody know? About 4.6. And the first life form was formed somewhere around 3 billion years ago. And the first animal is 0.5, so it took a while. So land colonization had happened December 24th. Okay? So you see lots of movies about dinosaurs, right? You may think it's a long time ago, but in terms of the history of the universe, it's not that long time ago. And does anybody have a guess?
December 30th.
29. Okay, you got it? And many years after the extinction of dinosaurs and modern human appeared. However, I wish to mention one thing. Do you know the cause of the extinction of the dinosaurs? Right. Do you know who discovered it or who kind of suggested? I'm asking them. Do you know the answer? So, yes. So extinction dinosaur, we didn't know, until Louis Alvarez, who was here, and then his office is still there. Actually, you can kind of see. Somebody, could you show his office?
For those of you that read The Three Big Bangs, that was one of the books I mentioned. It talks about his story, and actually he was kind of poo-pooed by the regular geology community, right? They didn't appreciate somebody sort of coming in from a different background.
So Louis Alvarez was a physicist here, and then he's got an office on the corner of the building 50, and his son was a geologist. And together, they kind of found a very strange layer all over the world. And that kind of indicated a big, massive explosion had happened. And everybody kind of laughed at them, but now evidence is solid. So we know the extinction of dinosaurs was caused by the big impact. Okay, so I want you to know that discovery had happened here. Okay, and the modern human appeared at the very last second. Okay, so the history of the human. Okay, this was, I calculated, about 10,000 years, because the modern human, we believe modern human appeared. The history is about 5 million years. The modern shape of our self appeared 5 million years ago, and the 10,000 years ago, modern civilization had happened. So it's just the last second. Okay. So compared to the size of the universe, our history is tiny. And in this scale, do you know how long your life would be? It's 0.2 seconds. So I wouldn't say nothing, but it's compared to the history of the universe, it's very, very tiny. So that's something I wanted to know. And here, I wish to take you to the travel to the space. So I'm going to take you from the solar system to the farthest universe which we know right now. And let me introduce from the solar system. And I suppose most of you know what the solar system looks like, but I want you to remind you what kind of things are happening to our research. So suppose the size of the sun is a quarter coin. What are the distance to the planet? And I'm going to introduce the planets we know. Okay? So let me start from the sun. The sun is, of course, our mother star, and it's very violent. It's rotating, orbiting, spinning, right? But in X-ray, it's very violent. It's got a huge explosion happening everywhere. And then this is when the satellites explode. The size of the Earth is, like this. So the sun is bigger, 109 times bigger than the Earth in terms of radius. Okay. So this is the, this is not the movie. It's kind of a simulated image, but it's happening right now. Okay. So on the surface, explosion is happening everywhere, and it's trapped in the magnetic field. And once again, the size of the Earth is like this, and then prominence, which is much bigger than the size of Earth, is happening every single day. Okay. And of course, it provides us huge energy. And the Mercury is the closest planet, and then in the my scale, suppose the sun is the quarter coin, it's 1 meter away, which is like this. Okay? And the Mercury is like the moon rock planet, and we don't know if any life form can exist there. Okay? And the Venus is a little bit strange. Do you know what's strange about Venus? Say it again? That's right. So the sun, as I showed you in the previous animation, is rotating this way, right? And the Earth is rotating this way. Other planets all rotating this way. But the Venus is the only exception which rotates backwards, and we don't know why it's happening. And from the Venus, actually, that distance from the Earth, the sun is 1.86 meters between the quarter point scale. And we know it's got a thick layer of atmosphere, and it's covered by carbon dioxide.
Is that distance measured from the center of the sun to the
Yes.
center of the Earth?
Yeah. And the reason why we worry about the global warming, warming is from this planet. So if we keep, having lots of carbon dioxide, the fate of the planet Earth is going to become like this. So we are learning what's going to be happening to the Earth from the other planets. Okay? Do you have a question? So, and finally, this is the Earth, and it's a beautiful planet. And what I tell astronomical unit is, suppose I have the distance scale measured from the sun to the Earth, how much this would be. So we use the distance from the Earth to the sun as a unity, and that's the astronomical unit. And in a coin scale, quarter coin scale, it's 2.58 meters, so from here to there. Okay? And the size of Earth is like the grain of salt. It's very tiny compared to the sun. Okay, verse it's a little bit further, 1.5 AU, and it's about 4 meters away if this is the quarter point. And as you know, about 3 billion years ago, the ocean existed, and there is a sign of the water on planet Mars. So we hope, and we kind of excited, there might be a sign of the life form on planet Mars, because recently we discovered water exists on this planet, and you might have, in the past, life form might have existed, and that's an interesting thing to the research. So if it is true, that means life could happen any place. So this planet, to do the research on this planet can give us a hint how many life forms can exist in the universe. Okay? And the next planet is Jupiter, and it's a little bit far distant as the Earth to the Sun. Okay? What is special about Jupiter is that it's got a 4 big satellite, Galileo Galilei satellite, and one big satellite named Europa has a very interesting structure. Okay, it's got this filament-like structure, and it's covered by this brownish color. And this might be a sign of some microbes or some sort of life form. And then we know it's covered by a gigantic ice. And some people is guessing beneath the ice there could be a huge gigantic ocean. So life form could exist on this satellite. So NASA has a mission to send a probe to this satellite, and depending on the budget, you may be able to see it. And that's another reason you should support, a great discovery mission like this. Okay. So once again, if life form is found, that is going to be exciting. In 1992, what happened? That means comet Shoemaker-Levy hit right on Jupiter. Okay, so I mentioned there was a deep impact which caused the extinction of the dinosaur had happened, but we didn't imagine we kind of can witness it. So it happened on Jupiter 20 years ago, and a few years ago, I think it's last year or 2 years ago, similar thing happened on Jupiter. So in fact, we realized Jupiter is a gigantic planet, and the researchers found Jupiter is indeed protecting the Earth because of the huge gravity. The comet is coming all over the place, but because of the huge gravity of Jupiter, it was attracted by Jupiter. So if Jupiter didn't exist, we could have more deep impact, and we couldn't exist. So because of the too many deep impact happened on Earth, so Jupiter is protecting us. So we need to thank it. Okay, Saturn is a little bit farther. It's 10 by 10 astronomical unit, but it's got a beautiful ring. So it's amazing how many layers this ring has. Few hundred or few thousand. And we think it's made of ice, and we believe it just phenomena happened only a few million years. It only lasts only a few million years or a little bit more. So what happened to this ring was a satellite or any astronomical object came close to the sun, came close to the Saturn, and it's got disrupted and it's destroyed. And it made a form of this beautiful ring. And eventually it's going to collide and it disappear. So we are very lucky to see this phenomenon. Okay? Okay, so you might have heard the aurora, which happens North Pole or South Pole, but the same thing is happening to the Saturn. So the charged particle from the sun travels and it's trapped either Earth or Saturn, and it's causing this beautiful aurora around the pole. Okay. So the next planet is Uranus, and we didn't know, we couldn't see this ring, but a recent study suggests it's gonna ring just like the Saturn. And then it's a little bit farther, 20 astronomical units, and then we believe it's a gas giant. Okay? It doesn't have it has a core, but it doesn't have, unlike the Earth, it doesn't have a solid surface. It's a gas giant made of the gas like hydrogen, helium. Okay? And one thing about special about this planet is the spinning orbit, the axis is tilted, which suggests it's got a huge collision in the past, and it's, I don't know how much energy you need, but it's got tilted like this. And the next planet is Neptune. We're getting farther and farther. Point is 77 meters away. Okay. And the next one is Pluto, and this is one of the controversial ones, as you might have heard. And I wish to make sure you did the homework, okay? What is special about Pluto? What happened recently? Say that again, Lyle. Yeah. Because?
Oh, it's too small.
Yeah. Not only too small, but also.
We found a lot of similar, like floating masses, like
Planets, yes. I'm glad you guys did your homework. So as what's your name? Andrew said there are lots of planets like Pluto. Okay, and astronomers found other planets like Selena, which is actually almost equivalent in size, and then it's got lots of them. So if you point the telescope to the edge of the solar system, you find lots of moving objects. Okay, hundreds of them. Pluto could be just one of them. But not only that, this is the Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. So these guys are on the same plane, okay, and they're orbiting on the same direction. Although, as I said, the Venus is spinning backwards, but other than that, most of the planets is orbiting on the same plane. That means they are formed in the same way. Okay? And the formation epoch is about 4.6 billion years ago, and we believe they are, brothers and sisters. However, Pluto has a it's got huge inclination in terms of orbit. And then we believe, okay, the formation could be just different. It doesn't belong to the solar system. That's why several years ago, International Astronomical Union, they voted, okay, Pluto is not the planet. So now we believe it's got a new category called the dwarf planet, and Pluto is just one of them. And then the new discovery is just like other systems that we keep, for instance, Keck telescope is finding lots of them. So we believe Pluto is just one of them. Okay? So now we believe Pluto is not an official planet, but it's a family of new category called dwarf planet. Okay? So that's the end of the solar system. So let me remind you the too far. So the Pluto is in a scale of the quarter coin. If the sun is the quarter coin, the Pluto is 100 meters away, and it's astronomical units, 40 times as distant as the sun to the Earth. Okay, so let's go to the next star, which is shining just like the sun. And then, can anybody recognize the constellation of this image? No. Yeah. So this is Southern Cross. Okay. So this is something we cannot see from the Earth because next time you travel to the southern hemisphere, please try to find this vehicle, Southern Cross. And this one is called Alpha Centauri. It's the nearest star to the sun or Earth. Okay. And then let me ask you the question. Suppose the size of the sun is a quarter coin. Where is this Alpha Centauri? So this is a multiple question. Okay. So I want you to raise your hand. 700 meters, which is about half mile. About 5 miles, 7 kilometers. San Francisco Airport. 1. Berkeley, downtown Berkeley. San Diego. Okay, you guys did a good homework. And the answer is San Diego. So the sun is here, and the nearest sun is in San Diego. Okay, and we know that our star is moving, but you don't expect. Whenever even if I throw a coin, I will never hit the coin in San Diego. So the star-star collision never happens. Okay, almost never happens. So it takes, the speed of light. How fast is the speed of light? Anybody know?
10 to 8.
Excellent. So it's very fast, and it says it can travel 7 times and a half of the Earth per second. So this is the fastest airplane on this planet, the high-tech airplane, and it's got a Mach 6.3. So if you take this airplane, how long does it take to travel to the nearest star? Okay, I want you to raise your hand again. 5 years, 50 years, 500 years, 5,000 years, okay, 500,000 years. Okay, you guys are getting good. The answer is 500,000 years. Okay, so you see lots of the scientific fiction movies or TV series, but it's hard to travel. So unless you invent something super, it's not realistic to travel to the other stars. Yeah. And then, as you know, it's very far. And then we have many stars. So this is the picture of galaxy, and we believe Milky Way galaxy looks like this. Yeah, and we are one of them. And then how many stars do we have in our galaxy? Okay, 2,000, 20,000, 200,000, 200 million, and then 200 billion. Okay, you are getting it, right? It's the answer, 200 billion. By the way, I have been doing this talk for many years by now, but nobody ever succeeded to answer all of the questions right. Okay? I want you to be careful. So the answer is 200 billion stars. So once again, the distance between the stars is so far. However, we got 200 billion stars. So you can imagine how big this galaxy is. The size of the star is now, I'm changing the scale, a grain of salt. 200 billion grain of salt will fill up what size, cup, bucket, a car, or truck, or Olympic sized pool. Okay? So the answer is Olympic sized pool. So imagine, we have many stars in our galaxy, okay? And then suppose the size of the sun is the grain of salt, it's going to fill up the Olympic size ball. It's a gigantic number, okay? So you imagine, the sun is hosting us, the life form. So you imagine so here is the does anybody know the name of the system?
Well, that's a bummer.
Yeah, that's right.
But just a question, just for scale. If the stars were a grain of salt and takes 200 billion, takes a Olympic-sized pool, what if you were to put that to scale and spread it out?
That's gigantic.
How big would that galaxy be?
I haven't done that homework, but you should do that calculation.
Would it be the size of the United States?
I think it's bigger than that. Okay, please do the homework, okay? So please assign the good homework to them. Okay, so this is the Andromeda Galaxy, the nearest galaxy to our Milky Way galaxy. And likewise, it's kind of sister galaxy, and we believe it's similarly, it's got 200 billion stars in this system. Okay, then I need to ask you a question. So suppose the size of our Milky Way galaxy is the quarter coin like this, which is made of 200 billion stars, and it's got a 100,000 light years across, right? The radius is about 10 kiloparsecs. So, okay, so where is the, suppose this is our galaxy, where is this nearest galaxy? Okay, so I'm going to ask you very San Francisco, New York, okay, couple, 1, 2, 3, 4, 5, 6, 7, and Paris. Aha. Someone knew the answer. Okay? The answer is 47 million. You guys got trapped. Except one. Did you know the answer? Okay. Did you cheat? So this is 2 million light years away, and if this is the size of the Milky Way, it's like here, right? And the galaxies are moving each other. That means, what's going to happen. So in terms of the scale of the distance, for some reason my animation is not quite working, but this is the simulation of galaxy collision. So galaxy could collide because, let me try again. Oh yeah, it's working. So because of the relative closeness, so it can collide and merge into a bigger galaxy. Okay? And you might think you're joking, but kind of see this is really happening. Okay, so look at this. This is the real picture.
What sort of time frame are we looking at?
This is several million years. Medium.
So the galaxies kind of orbit each other before they go? Is that what's happening?
Some are, orbiting with each other, and then
Is it because they're close?
close.
Or what
And
makes them come together?
so there are lots of things going on because we believe in the universe, and our galaxy is made of these fluctuations of the mass, and there are lots of small galaxies in the past, and they are randomly moving. So some became close and they trapped each other and they make a spiral and they collide again. Some keeps colliding. As you might have heard, we got a satellite galaxy. Can anybody name the satellite galaxy of a Milky Way system? You guys have heard. You can see it from the southern hemisphere. Say that again. So you guys know it. So it's called Magellanic Cloud, and then there's two Magellanic Clouds. One is large Magellanic Cloud, and the other one is small Magellanic Clouds. And it's a very dwarf galaxy, but we believe it's orbiting or connected to our Milky Way system. And our beautiful system is formed after these collisions.
Are those planets? What is it?
Clouds? Stars, yes.
So are they, you said like the distance between stars?
Yeah.
Are they like
Stars is here and in the San Diego, and the star never collides.
so the stars are just moving around each other?
Right.
Eventually, the nuclear will collide?
No. A nuclear or galaxy could collide, but the stars will almost never collide with each other because of the distance.
I guess the question is there any matter colliding with matter when two galaxies form? I mean, at least in an immediate sense.
You mean the matter, like dark matter?
No, just regular matter.
Regular matter. Okay, the regular matter is kind of mixed, and the gas can be mixed, but the star never gets collided with each other. Am I answering? Yeah. So it's making a mess.
Maybe the question is, in the center of the galaxy,
Yeah.
the stars are closer together
Yeah.
than they are
Right.
in our neighborhood.
Right.
But they're still so far apart.
That's right.
Oh.
Right. And then we really we kind of expect, we know the core of the galaxy is we have a black hole, and the black hole collision could happen. However, we don't believe, we don't think star-star collision happens because the lifetime of star is not too long. Okay? And then it explodes, as you will see in a minute, and then it disappears. So this is one of the colliding galaxies, and then it's called antenna galaxies. Beautiful galaxies. So from the like a big picture, you got two big tails and a core. This is a Hubble Space Telescope image, and you see two cores colliding with each other, and you see lots of blue dots, right? Just like the human interaction, if you collide two things to each other, and the gas is compressed, and then once gas is compressed, you will see lots of star formation. So this blue star is the sign of the star formation. Okay? So the collision of galaxies induces lots of the star formation. And in our system, even our system, I mean Milky Way galaxy, we see the stripe of stars in the past, and the recently thrown this survey revealed that our galaxy collided with the dwarf galaxy. So this is not too rare. It happens quite often.
If the galaxy collided with Mars, would life be exterminated?
No. Like I said, I think star-star collision doesn't happen.
Well, not like that. I mean, like, would the Earth be exposed far enough away from the sun,
No, it doesn't happen. So our solar system is a confined, system, and I don't think it happens. Right?
So if my galaxy collided with another, how would we know?
How do we know?
Yeah. There's nothing between.
Nothing changes, but you see lots of stars are coming. Actually,
Just get more
so in
stars.
fact, did I? Oh, no, I didn't make a slide. Okay, we believe our galaxy is heading towards Andromeda galaxies. Okay, if the human race can survive next few 100 million years, we can see the Andromeda galaxy is getting bigger and bigger. So you see two Milky Ways on the sky, and then, but Milky Ways is not that bright, right? We don't tell it's colliding, but you can see, nothing happens to us, I believe, but lots of star formation is happening. So maybe you can see lots of new stars forming.
Are we gonna see the other big star as another sun, like two suns?
Okay, so if our system is born in a double star system, yes, but like I said, it's very rare another star is trapped by another sun. So double star is originally, we believe that double system, we see lots of double star or triple stars in the system, but we believe it was formed at the same time. So they are sisters and brothers. However, just like you said, another star is coming into your system and it trapped and we rotate orbit with each other. It doesn't happen quite often. I think even if it happens, but the chance is very rare. So
if each galaxy has a black hole in the center, would these black holes collide? And if so, have there been models worked out on what would happen?
yes, great question. So stars has a lifetime, so stars can disappear, explode and disappear, but black hole doesn't disappear because we don't have a mechanism to destroy black hole yet. So black hole collision could happen eventually, and we believe it's a great source of the to detect the gravity wave, because a gravitational wave, because when it collides, it's going to form a gigantic black hole, and we believe, based on the Einstein's theory, it's going to emit gravitational wave, which human being never detected. But there is a mission called LISA, which is a satellite mission, and we believe that satellite mission can detect that gravitational wave. So this is one of the very active research area. And then Eric Linder, who is sitting over there, is one of the leaders to make a prediction of the black hole collision and use of cosmological measurement. Correct? Okay, so this is another sign of the beautiful sign of the galaxy interaction. So we believe white and dwarf galaxy collided onto this system and disrupt it and make a gigantic tail. Okay? So galaxy collision could happen many times, and our Milky Way has a sign, and we see this collision quite often in the universe. Okay? Any questions? So, okay. So this is the biggest image of the universe. It's called the ultra deep field, and everything you see is a galaxy. Okay? So the Hubble telescope spent several hundred hours on this small tiny bit. Actually, this is about 100 times smaller than the size of the moon, and everything you see is the galaxy. Okay? It's very hard to find stars, actually. I see only several stars from 1, 2, 3. These are stars. This star belongs to our galaxy. But everything else is its own galaxy. Right? Once again, if I count this galaxy, it's got few billion stars, a few hundred billion stars. Okay? Another galaxy, this one is gigantic, so we have more than 200 billion stars. And then you see these tiny dots, right? And these are all small galaxies. And then the reason why some galaxies are red is because it's farther, it's a red shifted. So this is what we call elliptical galaxies, and it's a bigger system than our system, our Milky Way galaxies, and it's got a billion. So in our universe, like I said, one galaxy has few hundred billion stars. And in the universe, we are hosting several hundred billion galaxies. Okay, can you do the math? So a few hundred billion stars times several hundred billion galaxies. Okay, that's the number of stars in the universe. Okay, so it's natural to believe something good is happening in our universe. Okay, so let me briefly introduce what we study. So we study cosmology, which is the study of the universe, how universe is created, how universe is evolving, how galaxy is formed, how structure is formed, and then contents of the universe. And then we wish to know the fate of the universe. And until recently, like 10 years ago, we didn't know the fate of the universe, but now we know the age of the universe and the contents of the universe and the fate of the universe very, very precisely. And the top one is the Einstein equation, and this tells you the geometry, and if you solve this equation, you can come up with this expansion rate is a function of density, curvature, and the cosmological constant. And this equation is meant to scare you, but when you go to the college and then you learn how to solve it, and then if you take physics class, you can solve this equation, okay? And then it tells you how the curvature, how the density changes in time. Okay, that's what we study. Okay, so let me explain the origin of the universe, origin of the elements. So this is what I studied when I was a graduate student, and let me introduce how we know how the elements were formed. Okay, at the very beginning of the universe, the energy, it was pure energy. At the very first minutes, 3 minutes, these elements were formed. Okay, so you see the table of elements from the chemistry class or physics class. We know it's got 100 elements on this planet, but at the very beginning of the universe, 94% was hydrogen, and 6% was helium in terms of number. Okay, so this is the diagram, okay, what we call baryon density versus the mass fraction and the number fraction compared to the hydrogen. So baryon density means, what we call baryon asymmetry means, so the pure energy has, pure energy got separated into particle and antiparticle. And there is a very slight asymmetry. And the most of them got collided with each other and then became photon, means light. And only a few particles survived, which we call baryon, which is your normal element atoms. And then the fraction was 1 in the 10 billion. Okay? So this slight asymmetry made us. So, and that's how we can calculate the amount of the hydrogen and helium. Okay? So I suppose you have been studying this table of elements. So at the very beginning of the universe, we have only hydrogen and helium. The rest of the element didn't exist. And as you know, alchemists in the 17th century failed. You cannot change the elements. You cannot make gold from other elements. Okay? But on this planet, we have many elements, many kinds of elements. So how do you make it? You guys know?
Synthesize them.
Yeah. So you did that homework, but not exactly. Okay. So there's a few steps. And I want you to know a little bit more exactly what happened to these history. So up to the iron, which is the 26th element, so the sun burns helium to hydrogen, and the helium turns into carbon and oxygen. And from carbon, you can make neon and magnesium, oxygen, and make silicon and sulfur. And at the end, you can make iron, which is the most stable element. Okay, so I need to find iron somewhere. 26 okay, yeah. So after here, you can make it inside the star. Okay? That's the nuclear fusion, and that's how the sun is shining. Okay, but beyond that, you see lots of elements. The solar fusion is not energetic enough to make this. And you have already mentioned that there is only one place you can make it. You can have this huge energy, which is, that's right. So the last element was created at the very end of the star. So these are the sign of dying star. So this is at the end of the star's life. It's releasing its surface gas into the space. Okay. Next slide. Okay, and when the supernova happens, in terms of few seconds, you can create a gigantic energy. Okay, then you can create the rest of the elements like silver, gold, etc. So I want you to realize that your body used to be inside the core of the stars. Okay. The things you might wear silvers and gold, used to be here. And it's a gigantic recycle system. Star explodes, star forms, star explodes, and star forms. After many cycles, finally we are here. So in the history of the universe, we used to be a star, okay? And then I want to introduce one of the images we got. So I want to take the question. You will recognize what this is, right? This is the Bay Bridge. And there's something special is happening. Does anybody tell? Or can I rephrase?
I know what it is.
Okay, great. Students, speak up. So this was taken at the certain date this year. No. No, not really good. What? It doesn't happen too often, so it's not. That's right, it's tsunami. So this picture is taken March 12th. Okay, the tsunami, the big earthquake had happened, in Japan on the. So in our time, it was happened in March 11th, 2 p.m. their time. That means our 10 p.m. on Thursday. And then Friday morning, I came to the office and I saw the ocean was separated in two parts. And it turned out to be, it was tsunami. Okay? So it traveled across the ocean in 12 hours, about. And then if you divide distance per time, it was like 720 kilometers per hour, which is about the speed of the jet airplane. It's very fast. And then we can calculate using physics. We can get to know the depth of the ocean. And if I do the calculation, it's about 4 kilometers. It's just square root of height divided by gravitational constant G 9.8. And then I can get to know the depth of the ocean is about 4 kilometers. And it's amazing. Okay? But I couldn't find a good picture, but for me it's a big technique. So the earthquake happens because of the thermal circulation inside the Earth. Okay? But do you know why this is happening? Do you realize, or have you thought, deeply why this is happening? What is energizing to make this, circle? Yeah, convection. But why it's convecting? Because why it's heating? What? Say that again. Not fusion. Fission, yes. So nuclear fission is happening. So nuclear fission is happening, and the nuclear fission, because of the nuclear fission, is this uran and plutonium, right? And it's rare, but it exists inside a very core of the Earth. Okay. So these elements, very heavy elements, uran, etc. Actually, it's uran, which is causing this. Is made when the star is exploding, and it was captured 4.6 billion years ago, and it's still hitting the Earth. And then we know we can take advantage of this Uran, and then we can do the nuclear fission, nuclear energy. And then in France, 70% of energy is supported by this fission. And then in Japan, as you know, Fukushima nuclear plant is taking advantage of this. But the earthquake, Uran could give us, huge energy. At the same time, Uran is causing us the earthquake. So behind this tsunami or plate moving around the Earth is caused by this element. Okay? And if you think very, very backwards, it was happening inside the star. So Uran could be your fate, could be your friend, or could be your enemy. But that's how nature works. Okay? And I suppose a week ago you might have seen lots of fireworks for the 4th of July. And we can study lots of things by looking at this. And I'm going to explain why. Okay? So you might have seen these beautiful pictures of nebula. And then color tells you something. Okay? So for instance, the red color, so each element has a specific color. So by looking at this red color, I can tell, okay, it's hydrogen. And if I see this green color, I see oxygen. So for instance, if I take a look at this fireworks, so this blue color is copper. This red color is strontium. So each element has its own specific color. So by studying these colors, you can study what kind of elements they are made of. So I did the calculation, and then, like I said, the hydrogen and the helium is made when the Big Bang had happened. So 60% of our element, your body, is made from the Big Bang. And the 35% type 2 supernova. Type 2 supernova can create carbon, nitrogen, oxygen, silicon. Okay? When you breathe your oxygen, okay, that comes from type 2 supernova, which is a big star explosion. Okay? And then your body needs some iron, and then 5% comes from type 1A supernova, which is a special type of supernova, the binary system explosion. And then, not only, if you think, okay, you come from your parents, grandparents, if you calculate, by the way, if you calculate 500 times your parents is your parents, every region comes to one family. And if I repeat the same thing 5,000 times, your parents, everybody in this room can come to the original 7 families. Okay? And then if I do the same question, what happened to the parents, and if I repeat the same thing like several billion years, you come up to the type 1A supernova, type 2 supernovae, and then if you repeat the question 13.7 billion years, it comes back to Big Bang. So you're made in the universe. Okay? And then, believe it or not, we can calculate this very, very precisely. So this is called spectroscopy, and we take the spectrum, and which is we divide color into many, many, many colors. And this is just one example of by a Hubble Space Telescope, and then we see this zigzag dips, right? And that tells you, location tells you which element you are looking at. And then depth tells you how abundant it is. And by measuring the width, you can get to know the temperature. And then this is based on the quantum mechanics, and you can precisely measure how many atoms are there at the billions of light years away from us. And then this is the Galileo Galilei and the Newton's telescope. We take the advantage of these, and then we do the observation. So let me introduce, I wish to mention one more thing, which is how we use this CCD and the charge coupled devices. And you guys use digital camera, right? And the efficiency of the Earth film, which we used to use, is about 2%. But these charge-coupled devices, which you use digital camera, has an efficiency of 80% to 90%. And then, does anybody know who formulated this? So that the thing we use, photoelectronic effect, which is used inside your digital camera, is formulated by someone you know. And I want you to tell me who that is. That's right. So it was Einstein who formulated so conversion. So we don't have, I tell you, we don't have a good control of photons, but we do have a good control of electrons. So we cannot record photon itself. So you need to convert photon information to electron, and that's what Einstein formulated. And inside your digital camera, this is happening. And you may think Einstein is somebody else, but you are using Einstein's technology every day.
I had a question about the percentages.
Okay.
What does that represent?
So you have, say, as you know, light is a photon, it's a particle. So you have 100 photons, and then in film, 98% is missed or lost. But CCD, you capture 80%.
So what's the value for the biological?
Biological has a little bit more flexible, so as you might guess, it's got a self-stability. In the dark, you see, you may lose something, but in a bright situation, you capture a lot, so it varies. So that's why I didn't mention that. But it's better than film. Okay. And then we use this CCD technology to be a astronomical instrument. And then we use another technology. So we use many technologies to measure the size of the universe. So I want to mention one more thing, which is that instruments. Instrument has different, the sound, right? But the reason is it's got a different combination of these harmonics. So this is frequency versus amplitude. Guitar, violin has a different combination of these harmonics. And then you see the cycles, period, right? And the individual instrument has its own cycle. And this is what we observe in the universe. I suppose George Smoot, George Smoot, who worked on cosmic microwave background. And then because of the vibration, you see these peaks. And that's how you can measure the size of the universe. Okay? And that's how we got to know 13.7 billion years. And it's the same physics, how instrument vibrates, when you play the guitar, when you play the violin, you see the different, lengths give you the different pitch. And that's how you measure the pitch of the universe, and that's how you translate the pitch into the physical mechanism. So this is another way of measuring the distance and the scale. And so let me finish up with the future plans. So UC plus Caltech is now planning to have a gigantic telescope, which is 30-meter telescope, and on the top of Mauna Kea in Hawaii. So we get a good design, and we are pushing hard to build this. And the European folks are trying to build another one, which used to be 100 meter, but because of the budget cut, it's about 40 meter in diameter. But this guy is a bit different because we believe these guys can change the history of human being because they can find the planets. Okay, and then I want you to know another great thing is happening right now, which is a Kepler satellite, which has launched a few years ago, and it's observing right now. And the UC Berkeley is one of the key institutions to make this happen. So the mission is to find the Earth-like planets, and the method is a microsolar eclipse, which this animation is going to show you in a second. So they are monitoring hundreds of stars, actually several thousand stars, I think. And then if Earth-like planet can come across right in front of the star, it's fainted just a tiny bit. So suppose this is the star, and then something crosses, a tiny planet crosses the right in front of the star. It gets a little bit fainter, right? And that's what's happening right now. And they are finding hundreds of planets. And then I think sooner or later we can find Earth-like planets. And by now we know several hundred planets exist other than solar system. So this is very exciting. And then the telescope, a big telescope, can get the spectrum of these planets. That means you can measure the temperature. If ozone can exist, if oxygen can exist, that means the sign of life. So in your lifetime, you can get to know if there is a sign of life form other than solar system. So that's something exciting. And then there is the just a final animation. I don't know how to. Okay. So can anybody recognize the constellation?
Orion.
Yeah, here is Orion, 3 bells, show bells, right? So this is the constellation from the winter. So, but if you go to the dark sky, you can see the Milky Way. Okay. So this is just a recapture of what we have discussed today, and I'm going to be traveling across the Milky Way to the neighboring galaxy. Okay. So this is not a Hollywood movie. You dim the light. So, if you look at the sky, it looks like 2D, but in fact it's a 3D. So this is made by Mike Norman, Professor at San Diego, and other friends. And you're traveling across the Milky Way. So this is the host nebula, and the red means you get the hydrogen. So that's a star-forming region. So most of the star is in the realistic scale. Okay? So we are traveling through the Rosetta Nebula, which is another star-forming region, and it's 7,000 light years away from us. Whoa. And then next, we're going to be looking at the end of the starlight, which is the Club Nebula. So Club Nebula exploded. This is the base of the star, and it became a pulsar, and it's at the center. It's pulsating. See, pulsating. That's the end of the star's life. And we live in Milky Way galaxy, which is a world spiral, and our solar system is located close to the edge, not the center. Okay? So our location is one of these spiral arms, and we believe it's got a bar structure at the center. So this simulation animation is very close to the reality. And then that's the satellite galaxies I mentioned, Magellan Clouds. And then we got the neighboring galaxy, Andromeda Galaxy. And this is M33. And this is another star-forming region. And I want you to notice, our galaxy doesn't exist alone. Our galaxy forms a group, and the group of galaxy has a filament-like structure. Okay? This is the M82, M87. I don't know. So you see the structure like this, and then this is called Virgo cluster. And then many galaxies are forming this group. And it's a 1D filament. And on the corner, it's got a gigantic cluster of galaxies. And this is what we call Virgo cluster. It's one of the biggest structures in the universe. and the galaxies moving each other, and that's why it's called collide to each other. And at the center, it's got a gigantic elliptical galaxy, M87. So this is 100 times bigger than our Milky Way universe, Milky Way galaxy. So that's the structure of the universe. And I have a dream, which is in 7 years we will find, Earth-like planets, and then in 15 years, if you have TMT, 30-meter telescope, you can find a sign of life. Okay. And then maybe in 50 years, we can send a probe, depending on how budget goes. And then we, for some reason, Congress all across this line keeps cutting the budgets. But if you do well, we can send a probe to the planet, and then maybe you can find an intelligent life form. I'm not dreaming. And then maybe in 5,000 years, you can meet them. Okay? That's all. Thank you very much. Table of elements, but element itself didn't exist. After 3 minutes, the element was formed, and then say a birth of the first star, and then a galaxy is formed after the first star, and of course our solar system was formed, and the life form appeared on Earth, and the first animal appeared, and these events, right? Animal begins to colonize from ground. So this life form had happened in the sea, in the ocean, and now we know extinction of dinosaurs, and we appeared finally. So this is called the Sagan calendar, cosmic calendar, and we translate this 13.7 billion years event into 1 year. So suppose we witness the Big Bang at the beginning of the universe, a Big Bang as the January 1st midnight, and they say we are at the December 31st, close to the midnight. So we're going to shrink 13.7 billion years into 1 year. Okay? So this is in the Carl Sagan's book. He did it, but back then, about 20, 30 years ago, back then he didn't know the age of the universe, but we know exactly when it happened. And then tour means in both ways. One is in time, and then one is in space. So I'm going to take you from here to the end of the actually, I would say, edge of the universe, and then from here to the beginning of the universe. So the universe is so here is today's menu. So travel in time and travel in space. You might have heard space-time, which is inseparable. So Einstein made a connection. Indeed, time and space is the same thing. If you are away 1 light year, that means you are 1 year away from there, and 1 light year away from there means in two terms in the same thing. And I'm going to show you what is going on at this lab and what kind of research we are doing. And then I'm going to briefly mention future plans. Okay. So here, we are not using the big facilities, but we don't need to always use the big telescopes. You can observe something very, very fun just from your naked eye. And there's something special is going on in this picture. Can anybody tell what is going on? So I took this picture one of these days, and something special is happening. You know it. Anybody? Just observe and find what's going on. Come on, guys. You know it. I can give you a hint, something about this. And then you might be able to see 50 shooting stars per hour. Okay? So at the morning, you can see lots of shooting stars happening. So if you get a chance, look up the sky in the morning, like 3, 4-ish, and then you can see lots of stars. Okay? Okay, so let me start travel in time. So, do you know the age of the universe? Does anybody know age of the universe by now? So when I was a high school student, I was told the age of the universe is between 10 billion years and 20 billion years. But now we know precisely how old it is. Excellent. So 13.7 billion years. So that was measured about 7 years ago, and it becomes more accurate, and we are now sure it's 13.7 billion years. So what would you say the 10 biggest events happened in the universe? Big Bang, of course. And then here is my list. So say Big Bang, of course, and the Big Bang nucleosynthesis, which is the first of the elements. So this is my listing. You don't need to agree with me, but I would say this is one of the 10 biggest events. So at the very beginning, energy was pure energy. So we didn't exist, of course. And then element, which you learn somewhere, in this classroom, shape of the shades. So on this special day, something special is happening. Astronomical phenomenon is happening, and I want you to tell me what's going on. Say that again? Yeah. But do you know why? How do you know? Okay, go ahead.
Are those all projections?
Yeah. Right. So you see crescent shape, right? So this is a pinhole projection of the sun. So the sun, if you take a look at the telescope, the sun is in a good shape. The crescent shape. So next time the solar eclipse happens, I want you to not only look at the sun, but also look at the ground, so that you can see the pinhole camera image. Yeah? The same thing is happening. So if you pay attention to this, everything in the crescent shape. Okay? So normal day it's just whole sun is round, but on this eclipse day it's a crescent. Okay? And I suppose you may have a chance to go camping over the summer. And if you are flexible, I want you to pick up the special dates, which is August 12th through 13th. And here is a special day for shooting stars.
It's my pleasure to introduce to you this morning your speaker, now Suzuki.
Ahead of time, though.
Oh, you got a couple. Well, you can start early.
Okay.
You want the 4 minutes? Okay. Now came to us as a postdoc almost 6 years ago. This fall it will be. His background was in doing some interesting fits to quasar spectra, and he transitioned very nicely into supernova research here. So now is what we call a postdoctoral fellow. That's where he started, and now you're a research scientist, I guess is your official title here at the lab. Now is the holder of for at least the next few months, the most precise measurement of the cosmological parameters with a paper that came out in just the past month, I guess. It's not even 1 month old.
It was accepted.
Accepted.
Last week.
Last week, okay. So it was
So it's
put out,
official.
so a good turnaround by the referee. And it's measurement using supernova as distance indicators, as Io discussed yesterday, using the Hubble Space Telescope. And now is going to give you a lecture this morning, what he entitles A Tour of the Universe, so that you get an understanding of everything that's out there, or at least most of it. So here's now.
Okay. Thank you very much, Peter, and it's a great pleasure to be here. So today I'm going to be discussing the tour of the universe.